Hello, everybody. I'm going to go ahead and get started. So I'm Michael Seaman. I'm the chair of the Santa Clara Valley, San Francisco section, and as well as the Oakland East Bay section. So we combine all three to create the San Francisco Bay Area chapter of the IEEE Power Electronics Society. I'd like to welcome you to our October meeting. It's going to be a good one. We have 5 excellent speakers. Perhaps even 7 if you consider the support behind them. But I'll tell you a little bit, start talking a little bit about our chapter, what the session is going to be about, some of the logistics, and how you can help out our all volunteer chapter. So the San Francisco Bay Area chapter is won 3 prestigious awards in 2017. We won the Santa Clara Valley Outstanding Chapter Award, the Region 6 Outstanding Chapter Award, that's the whole Western US, as well as the Worldwide Power Electronics Society Best Chapter Award. So with that background, we'd like to present today's talk, an integrated virtual seminar entitled Integrated Power, a virtual power panel session. We have Steve Allen from PSemi, Wanyong Kim from Lion Semi, Stephen Oliver from Navitas, Noah Sturkin from Ferric, and Kirk Bresniker from HP Labs or HP Enterprise. So everything's going to be starting right now. After my talks, I'd like to thank our corporate sponsor, Navitas and Lion Semi, for their gracious donation to the Pell Society, and that helps us facilitate these large webinars and provide food once we get back to doing these things in person. Thanks to our 2020 officers and volunteers for the Pell's chapter. I'm the chair, Jason Poon's the vice chair, Ed Massey, secretary, Fei Shui is the treasurer, Doug is our program director. I'm also the webmaster. Mikhail Guz is our marketing director and social media expert. Doug is also our education director and site sponsor when we have meetings at Google. Kevin Cameron is our AV director, and we have several members at large, including Brian Zonstecker, the largest member at large, you could say. One announcement I'd like to make is that our open call for nominations for the election this year for officers next year is currently underway and is closing tomorrow. So if you'd like to get involved, run for chair, vice chair, secretary, or treasurer, please email Mikhail at the email address here, or any of the officers, and we can connect you to Mikhail in order to put your name in. If you're interested in volunteering in some other manner besides an elected position, we have an infinite number of spots for members at large where you can help us organize meetings, finding speakers, and promoting power electronics. So go ahead and email myself or Brian or any of the officers to learn more about getting involved. We are also looking at sponsorship. We have 2 great sponsors for this webinar. The sponsors include having promotional material and also helping out our seminars, and for in-person meetings, we can also support tables for networking and demonstration. So please check out our website. It's a lot easier to just Google SF-BAC PELS, and you'll learn about all of our upcoming events, as well as getting the slides and the videos from past events. You can also follow us on Twitter at SF-BAC PELS, where you can see all of our upcoming events, as well as general commentary about the power market. The eGrid is a Santa Clara Valley-wide, or maybe SF-BAC-wide publication that shows all of the electrical engineering IEEE events going on in the Bay Area for the next month or so. So it's a free email delivered to your inbox about twice a month, and it gives you great information. So you can go to egrid.biz and sign up for this. All right, so this is our first webinar in quite a while. So just as a request, so it's going to be start with 5 10-minute presentations or position statements, and then we're going to open it up for discussion amongst the panelists and take questions from the audience. So you can submit your questions anytime. We'd like to certainly get a few questions lined up before the presentations end. You can either direct them to a specific speaker or the panel as a whole. And use the Q&A button in your Zoom is the best way of answering them, and we can answer them most likely over audio. And Brian and myself will be doing the question selection, find the most interesting questions, and posing them to the panelists. All right, so thanks for the attention for the introduction. Let me go ahead and introduce our first speaker. So Steve Allen, I'm going to transition the slides over to him. Steve Allen has 40 years of experience in power conversion, with approximately 20 years in power modules and the remainder in power management ICs with 3 startups: Empyrean, Powervation, and MIT spinout Arctic Sand, now acquired by Murata through their semi-RF semiconductor division. He currently leads the power semiconductor business unit, developing bucks, boosts, and charge pumps based on Arctic Sand technology using advanced packaging technology. He holds an MBA with distinction from Bournemouth University and a BSEE at Portsmouth. So thanks, and let's welcome Steve.
Thank you, Mike, and hopefully everybody can hear me here. And thank you very much for the opportunity to make a position statement here. Basically, I'm going to be talking a little bit about architectural innovation and how that can really help to do integration for power. I think it's a critical step forward for power conversion. So to kick off, I'm going to just talk about what I think is a problem that any power engineer sees or platform engineer sees today, which is there just isn't enough room on the board and power is taking up too much space. It doesn't shrink with Moore's law. So power conversion, it has been shrinking a little bit in size, but still today, and this is a motherboard for...
Hey, Steve, sorry to interrupt. Can you make sure you're sharing your screen?
Oh, I'm sorry. I do apologize. Let's see if I can... For some reason, it just jumped straight into... I do apologize.
That's how integrated it is.
It's how integrated it is. All righty. So can you see it now? Is that okay?
Yes.
I'm just going to put it in presentation. Yeah. I do apologize. So, I'm showing a motherboard here for a notebook computer, and the red area is power conversion, yellow is inductors. Typically, we see with customers at least 25–30% of a circuit board is occupied by power conversion. In higher end platforms such as core routing, 5G, and so on, it can be more like 50–55%. And typically it's the inductors which is the largest component and also sets sometimes the profile, the height of a platform. And it's the one component that now dominates the bill of materials, and typically in a buck it's occupying about half of the actual footprint compared with all the other components that makes up that buck converter. Not only that, but if you look at the backside of the board here, this is all the input and output filtering, lots of pos caps, tantalums, and so on. And, you know, I work for Murata and a big player in capacitors. We like selling capacitors, but this is a problem that we see. Is it's not just the power solution, but it's also all those other additional components, both on the input and output, that eats up a lot of board space today. So where we see a problem is with that inductor, and this is just a little bit of simplified math. There is some more detail behind these two equations here. On the left-hand side, we're showing a toroidal inductor, and on the right-hand side, you have a MLCC. And the equations beneath these are showing the energy density for those two components. And we used a couple of examples here of a thick film barium titanate MLCC and then a nickel zinc ferrite toroidal. A key part of this equation is the permittivity and permeability, and in a vacuum, capacitors are about 142,000 lower value than what you see with an inductor. And that's critical if you kind of plug numbers into these equations and roll it out the other end for different types of capacitor and inductor. You really want the lowest possible permittivity or permeability. And what you end up with is, we've done quite a few worked examples, is doesn't matter what type of materials or components you pick, typically the order of magnitude is 400 times better energy density with a capacitor versus an inductor. So if you can do work using the capacitor, you're going to be able to help solve that space issue with the inductor that's typically taking up such a large amount of board space. So how do we kind of go after that issue? Well, we use capacitors together with a traditional power conversion architecture. It can be a buck or a boost. I'm showing an example here of step-down buck going from 12 volts to 1 volt. But the power flow could be reversed. It could be a boost as well. You could go from 1 volt at the input to 12 volts. But we put into this a charge pump stage. We show it here as graphically as a transformer stage, but it's effectively a virtually lossless stage using capacitors as a charge pump to do most of the work. And when we say virtually lossless, we're referring to about measured in a boost 99%, and in a buck about 97 to 98%. And we can also disaggregate that charge pump and use it as a standalone component, also to do work as a standalone element, so you can then put downstream regulators and so on. One of the key things that this brings to the table is that we can detach the relationship between input voltage and output voltage as far as efficiency is concerned. So we're not so worried about duty cycle. We can change the ratio of the charge pump. Here we're showing divide by 3, but it could be divide by 4, divide by 2. Efficiency of that charge pump stays the same. And so you can make the intermediate voltage that you see of 4 volts. That voltage can stay pretty much the same, almost independent of what your nominal input voltage is. And so we're also, through this architecture, doing most of the work using capacitors, and we're offloading how much work is being done by the buck. And other things that we're doing here as well is we actually use low voltage FETs throughout the whole powertrain. Even though this is a 12 volt buck, we don't need to use it with the architecture that we're bringing to market here. So we can do everything then, if we use low voltage FETs, we can do everything in a standard CMOS process. So to kind of show that pictorially, traditional solution here on the left, everybody's very familiar, I think, with the buck. You have an upper side, lower side FET, an inductor, an output filter. You've got other components, obviously, around as an input filter as well. But those FETs are rated for V in. They're holding off voltage. You're doing all the work on the inductor. And for a low duty cycle application, you're going to see a lot of input current pulses as well, which means you need a fairly large input filter. And that larger output inductor also limits how fast you can work with transients. If you want to really improve transient performance, apart from architectural things you can do with your controller, you have to start thinking about maybe pushing up crossover frequency, switching frequency, and so on. So our solution is to put the charge pump in front of the buck, and I show it here diagrammatically as like a staircase, because effectively what we're doing is we're moving voltage in small steps through the charge pump, and we're using caps to hold off voltage. And each of the FETs in our powertrain only sees the transition voltage, the step, as it's moving voltage down through the charge pump before it gets to the buck. So this is an interesting reverse of what a traditional buck does. A traditional buck holds off, the FETs hold off the voltage. Here we're effectively using caps to hold off voltage, and the FETs see the same voltage throughout the entire powertrain. Why do that? Well, there's a couple of benefits. We can use all low voltage FETs. We can build it in standard CMOS, but we can also run those FETs faster for the same switching losses as a traditional single stage buck. And the benefit there is that we can already start to shrink the inductor. But bear in mind also that that inductor is also doing a lot less work. It's only having to deal with a duty cycle of typically 25 to 50% compared with maybe 10% in many applications. And we're using capacitors, which, going back to the earlier slide, they can do a lot more work in a much smaller space. So we can use tiny chip inductors to do the vast amount of the power conversion work here. There is an extra benefit here is we can then start thinking about some novel things with the charge pump when we actually phase interleave that. So it's two charge pumps working 180 degrees out of phase. So we're pulling current out of the input almost continuously. So I wanted to show you a few examples of what that can do as far as integration and taking advantage of 3D packaging. And the first example I'm going to show you here is an LED boost. This is a 10-watt boost where we have integrated the die into the substrate. It's embedded directly into the substrate. And we just put the rest of the components on the top of the substrate. The substrate is about 300 microns thick. The terminations on the bottom side here of the part. And on the bottom side, the pads are actually copper directly up to the die. So we get a very good thermal attach. The total assembly is 7 by 11 millimeters, 1.6 high. It keeps very high efficiency. And the point to note here is if we were to do the same thing using a traditional single stage architecture, the inductor would have to be about 5 by 5 millimeters with a 1.2 millimeter height, which makes it obviously a much larger module. And all the power module guys today are struggling with this issue of how to shrink that inductor because it's a problem component. Incidentally, even with that larger inductor, the efficiency of the solution, even though it's larger, is quite a bit lower than this solution. We're talking about 3% with a large inductor, and if you shrink the inductor to try and get it into the same kind of package, you're going to end up with low 80s, which is an unacceptable performance for something which is 10 watts output. This is how it looks as far as stack up is concerned. It's layers of insulation material, laser etched, and then we have layers of copper plated directly to the die. So there's no solder to the die, and layers of copper above and below the die in intermediate layers. It's not possible to see that clearly with this little illustration here. But basically it gives us a very thermally good solution with very, very low parasitic losses. Another example, if we look at the charge pump that I mentioned earlier, if we disaggregate that and just focus on how good can we get it with just doing work using capacitors. This is an example of a 72 watt, 48 to 12 charge pump. 48 volts is very popular today for datacom applications and data centers. It's using the same kind of construction. We bury the die into the substrate, and we just put all of the passives on the top side. This is all the flying capacitors around the charge pump. The copper pads on the bottom side here have big copper slugs that go directly up to the die through the intermediate layers. And the power density of this solution is 6.5 kilowatts per cubic inch. And to put that into perspective, the nearest inductive-based solution, is actually the kind of leading product right now in the marketplace, is effectively about 2/3 of the power density, 4 kilowatts per cubic inch. It's a larger output power, but of course, once you've got a larger assembly, you're kind of limited as to where you can go put that. It's a higher product than this. This is just 2 millimeters high, so you can kind of spread it around on the underside of your boards. So it gives you some idea of what you can get. And the important point I want to make here is that we're at the starting post here. I mentioned that, capacitors can do 300, 400, 500 times better energy density compared with an inductor. But we're not getting anything like that out of capacitors today. There's a lot more that we can do to further improve on power density. And capacitors provides us with a very long runway. So to conclude, I think a lot of people are very familiar that 3D packaging is here and is already pretty much becoming mainstream. There's a large number of companies out there offering multiple die in substrate, passives in substrate, and so on. But getting the most benefit out of that packaging technology, we believe requires also innovation in architecture if you're not going to trade off performance. If you just take a traditional buck or a boost and try and squeeze it into a package, you're going to have to trade off performance because you're going to have to shrink the inductor to make the product small enough. We believe that capacitive-based architectures are gaining ground. Arctic Sand, the company that I came from, is now part of PSemi, did a lot of pioneering in the area. Now we're seeing a lot of companies all focusing on capacitive-based architectures, primarily for the same issues. It gives you higher energy density possibilities. And there's substantial scope for further improvement in passives, inductors for sure, but particularly capacitors. There's a big opportunity there, we think, to further drive smaller and more efficient products. So that's my pitch. Thank you very much for your time.
All right, thank you, Steve. That was a great introductory positioning statement. Let's move on to our next panelist. Won-Young Kim is a co-founder and CEO of Lion Semiconductor, a power IC startup based in San Francisco with offices in Korea and China. Lion Semiconductor has shipped more than 50 million switch capacitor power ICs to top-tier smartphones, leading the market in switch capacitor power ICs and expanding rapidly to many high-volume customers. Please go ahead.
Forgot to unmute myself.
Okay. Can you see your screen, so you're good to go.
Okay. So yeah, I would like to talk about how switch capacitor power ICs are being widely used and increasingly more widely used in mobile devices nowadays. So reducing heat dissipation is key for both charger ICs and DC-DC converters inside mobile devices. So for charger ICs, the problem is that the charging speed, if you want to charge fast, but there's too much heat dissipation, the phone often throttles the charging speed because you need to reduce the heat dissipation. For DC-DC converters as well, the same issue. So if there's too much heat coming from the DC-DC converter or even the charger IC, actually it doesn't just affect like charging speed or the power ICs, but it can affect things like processor speed. So the processor doesn't have enough heat budget if all these other components are burning so much heat. So the DC-DC converter with low efficiency could affect processor speed as well. So this is especially important in thermally limited mobile devices. So smartphones, definitely there's very, very little budget for heat dissipation. There's no active cooling in there. The device is very thin. And maybe to a lesser extent, but also in laptops, especially in the ultra thin laptops that are very thin and also extremely limited cooling mechanisms. Basically, it's the heat dissipation that dictates a lot of things. Like even if you put in a 100-watt rated processor, if it cannot run at 100 watts because of heat dissipation, you're not going to get that processor performance. So switch caps, just like our previous panelists explained, can offer very, very high efficiency compared to traditional buck converters using inductors. And so as a result, it offers faster charging and longer battery use time in mobile devices. So we've seen switch capacitors with efficiencies around 98%. And in a similar socket, the traditional buck competitors are about low 90s percentage. So in terms of power loss, it becomes the traditional buck is about 8%, switch cap is 2%. So the power loss of the switch cap is actually 1/4. So the heat dissipation is 1/4. And as a result, switch cap chargers can do 4 times faster charging or 4 times the power of charging while maintaining the same heat dissipation. And the 6% higher efficiency means that it's lower power consumption, so longer battery use time. And as I mentioned, also higher processor peak performance because the heat dissipation is lower. And then lastly, it's hard to do an apples-apples comparison, but just when we compared against one of our products against the competing traditional buck converter, the PCB area was about 1/2 and the Z height was about 1/4. Now Z height mainly because, actually the PCB area as well, mainly because the inductors tend to be very thick, whereas all of our products, we use 0402 or 0603 capacitors. So they tend to be all under 1 millimeter Z height and occupy very small PCB area. So here's a traditional charging path inside a mobile device without switch caps. So on the top is the wireless charging path and the bottom is the USB or wired charging path. And so wireless charging, it has about 10 volts and 1.5 amps through the wireless coil. And then it goes to a buck charger, which is about low 90s percentage efficiency. Same thing for USB. It has about 5 volt input, 3 amp cables, and it's 15 watts going to the battery. Now, as people tried to increase the charging power, they had to either increase the current or the voltage. And increasing the current can be very difficult because the wireless charging coil has a very high resistance. So if you increase the current, there's too much I²R loss. And also for the USB charging, the USB spec has, typically you don't want to go above 3 amp charging. So there is a limit to how much you can increase the current. So the answer is increasing the voltage, but then if the step down ratio gets higher, the buck converter will not have good efficiency. So here's an example of a new charging system with switch cap charger ICs. So the blue boxes are all the switch cap charger ICs. And now you see that we're up to 20 volts on the wireless charging side. And the current is still at 1.5 amps, but because it's 20 volts now, it's 30 watt wireless charging. And we have a 4-to-2 DC-DC. So 4-to-2 just means that it's a 4S to 2S. So 1 equals a 1S battery voltage. So this 4-to-2 switch cap has about 98% efficiency. And there's a downstream 2-to-1 switch cap charger that also has about 98% efficiency. So overall, the wireless charging efficiency becomes about 96% and wired becomes about 98%. So it's much higher efficiency compared to a low 90s traditional buck converter. And this is not some example that I made up. This is actually inside some of the smartphones that we are selling into. And you can see that all these blue boxes, they're new additional ICs. Like they're not replacing existing charger ICs. Their customers are actually buying new ICs to implement new charging systems with higher charging power. So here's a measurement result of a Xiaomi phone where it uses a 98% efficient Lion IC to enable faster wireless charging compared to a Samsung Galaxy Note 10, which is a traditional, uses a traditional buck charger. And on the top is the charge percentage across time. And the middle plot is the current going into the battery. And then the bottom plot is the temperature. And so what this shows is that actually the charging starts to throttle when the temperature reaches a certain limit. So you can see that even in the Xiaomi Mi 9 Pro using our chip, it doesn't stay at the 6 amp battery current for a long time. It actually needs to throttle and then go back up again and come down back depending on the temperature. So yeah, this really emphasizes that how efficiency is important. So this is kind of connecting to our previous panelist about maximizing efficiencies with switch capacitor power ICs. So the first thing is it's better to minimize the number of inductors in the power path. So one inductor just for the fine regulation, and bulk of the conversion can be done with a switch cap. So for example, instead of using a 20 volt down to 1 volt buck, for example, use a 4-to-1 switch cap followed by a 5 volt to 1 volt buck. Or another example is in the charging case, actually, because the AC-DC wall adapter with the inductor provides regulation already, the conversion inside the mobile device, smartphone or laptops, etc., can all be done only with switch cap. It doesn't need an inductor. And the second point I want to emphasize is that switch caps are already very much widespread in mobile devices. So just our company, we shipped 70 million ICs in the past 2 years. We're on track to ship 100 million by the end of this year. And there's a ton of need, like very rapidly growing need for more advanced switch cap topologies in mobile devices. We see customers saying like, hey, like 98% isn't good enough. We need to get to like 98.5%. Just really like they're fighting for 0.1% like more efficiency, because once you get to like tens of watts in charging, then like every single 0.1% is actually very important in reducing heat dissipation. So that's the end of my presentation.
All right, thanks, Won-Young. That was a great talk, and I think we've seen 2 presentations already about how switch capacitors can help push power density and efficiency. So before we go into our next, I think I'd like to remind everybody that we do have a Q&A. It's used by the Q&A button at the bottom of Zoom. There's really going to be a queue right now. Please enter your questions. We already have 3 great questions, and we can we'll put those all together and ask the speakers at the end of all the sessions, and we'll have probably about an hour to do open discussions. So I recommend using the Q&A and not the chat if possible, and that'll let us more easily address the questions. So they'll all be addressed at the end of the talk. If there's kind of some details about it or some detailed questions that aren't necessarily good discussion questions, we might answer them via text. So just take a look to see if your question gets answered that way. All right, so let's go ahead and move on to the next speaker. Stephen Oliver is VP of Corporate Marketing and Investor Relations for Navitas Semiconductor. He has over 25 years experience in the power semiconductor and power supply industries in computing, industrial, automotive, and telecom markets with Motorola and Philips or NXP, and IR and Vicor in the US. He holds a Bachelor of Engineering from Manchester University and an MBA from UCLA. Stephen holds several patents in power semiconductors, is a chartered engineer, and has been VP, President, and Chairman of PSMA. So let's welcome Stephen. All right, thanks.
Thank you very much. And I'd also like to introduce Mr. Dan Kinzer, who is co-founder and Chief Technical Officer and Chief Operating Officer for Navitas, who will help me with the tricky bits. So today we're going to talk about integration of GaN-fast power ICs. Obviously in the name there is GaN, that's gallium nitride, and Navitas is the first and only GaN power IC company. So a quick introduction. So Navitas, we have a main design center in Los Angeles, or El Segundo, which is next to Los Angeles Airport. We also have design and support and application centers in Shenzhen, Hangzhou, and Shanghai. The design of the GaN-fast power ICs uses a proprietary PDK, that's Process Design Kit, and it is a GaN on silicon construction, and we rate our devices at 650 and going up to an 800 volt peak. So this is 800 volt gallium nitride. Part of that work over the last 6 years since founding in 2014 has been the writing and claiming of 100 patents. You can see the patent wall on the top right there, that's in our office. Once all of the virus is gone, we welcome you with open arms to come and visit us. For the manufacturing flow, we are a fabless semiconductor company, and we use TSMC in Hsinchu, that's Taiwan. They're doing the GaN on silicon on 6-inch wafers. And one of our packaging suppliers is Amkor, and we're using the Philippines factory for 5x6 and 6x8 millimeter power QFNs. We have a lot of capacity, and so far we're ramping very hard, and we've shipped more than 8 million of the GaNFast power ICs. In terms of quality, we are beyond the original JEDEC specifications. With the new technology, we realized that we had to test it in new ways so that it would be robust for the customers. And so we discovered certain new tests that we had to do and implemented those. And those have been part of the founding of a new JEDEC subcommittee in gallium nitride. And we're very pleased to say that we've had 0 field failures from those 8 million pieces shipped. I'd like Dan to take the next one.
Okay, thank you, Steve. And thank you for everybody who is here listening to this presentation. From the beginning of our company, we were interested in exploiting the excellent properties of gallium nitride. As you can see, the electric field capability is about 10 times that of silicon. So you can handle more than 3 megavolts per centimeter of electric field, which means, 100 volts per micron, 300 volts per micron. So, a lateral device that has 900 volt capability in theory only needs about 3 microns. It takes a little bit more than that in practice. But GaN is also a horizontal or lateral device that's all formed on the surface. The silicon is really just under there as a mechanical substrate and a lattice structure that you can use as a seed for growing the gallium nitride layers. So you can scale the voltage, you can make enhancement and depletion mode devices, and you can integrate quite a number of passives. And using those devices, you can integrate many different types of circuits. We've put a lot of effort into making the most of those, that kit of devices and integrating what we can. You also get extremely high mobility up to the range of 2,000 centimeters squared per volt second, so well above silicon. And you can also have a high carrier density in the so-called two-dimensional electron gas, or 2DEG, that forms at the AlGaN-GaN interface. This particular device has source-connected field plates and a gate that is formed from a P-type gallium nitride layer. It's all integrated on silicon, and it's built in a CMOS compatible 6-inch fab. In fact, it is a CMOS fab, so it's quite low cost manufacturing. Next one, Steve. The capacitances are quite low. The switching frequency can be extremely high. The gate charge can be about 95% less than comparable RDS-on silicon superjunction device. The particular device that we use is an enhancement mode device. It means normally off. It's quite a bit faster and lower gate charge than a cascoded GaN device that would be formed with a series connected GaN and low voltage silicon FET. So the technology is very fast. It can operate at high frequencies up in the tens of megahertz if needed or desired. But beyond that, we learned how to make these other circuits and, integrated many drive and control functions, protection features, gate voltage regulators, level shifters, a variety of other circuitry to make single switches, half bridge, configured switches and so on, and all done monolithically on a GAN chip. Next one, Steve. So we talked a little bit about the GAN physical performance. Wide band gap, which is kind of a buzzword these days, mostly applies in silicon carbide and gallium nitride. GAN is similar to silicon in thermal conductivity, but it has that high electric field and high mobility. We chose, as I described earlier, the E-mode FET path. Some other companies have also gone that way, companies like Infineon, EPC, Panasonic. Other companies have gone the depletion mode way or the cascode way, like Transform, for example, Texas Instruments, Power Integrations. But no companies have really gone as far as we have, and especially not in high voltage, to integrate as much functionality into the chip in the drive, control, and protection of the device. And with that, I'll hand it back to Steve.
Thanks, Dan. So we've looked at the structure of the device and we've looked at some of the components in there. And now we're looking at how they operate within a system. We briefly mentioned the quality of the field results. And one of the reasons for that is because we've built in many features that the designer can use to protect the total circuit. So as you can see here, this is what we call one of our single devices. We also have half bridge, and you can see that we have the gate directly tied, sorry, the driver directly tied to the gate of the GAN FET. This is one of the key items. This is a monolithic integration, all of it in GAN on silicon, and that gives us some very good performance we'll talk to in the next couple of slides. The GAN fast power ICs are digital input, power output building blocks. So with digital input, power out, very easy to implement in a circuit and very easy to get very high frequency performance. All of the devices are rated at 2 megahertz. In terms of that gate driver to gate loop, if you have a discrete device, then there is a natural impedance in the gate source loop. And that means that you can have, first of all, loss or erratic behavior in that system because of frequencies that we're trying to achieve. But if you have that monolithic integration, then that gate source loop impedance goes to 0, and you have very fast performance with a very stable output. And to put that in more detail, if you have an external driver, you get the oscillation. If you try to put some gate resistance in there, it slows it down, so you're stable, but it's also very slow and lossy. The integrated driver, you get 10 times faster with 0 loss and a very stable performance from that integration. Now, what does that mean in a circuit? This is one example. This is from the Oppo company, which is one of the top companies for phones in China and different parts of Europe and the world. This is an example of using high frequency performance, not only to reduce the main transformer from a bulky toroidal design to a planar design, which also helps with EMI performance, but also in this case, because that's implemented with a what's called a pulsed active clamp flyback, we can also eliminate the electrolytic bulk caps and make the whole thing very small. So in this case, this is a 50-watt cookie charger, because it's the same size as a classic Chinese cookie, and it's only 10.5 millimeters thin, including the case. And this also is a proprietary Oppo design with direct charge. So every time there's a gap in the pulse, we're eliminating the polarizing effect within the battery structure itself, extending the battery life. In the abstract, we talked about the commercial side also. So looking at where you can go with high frequency GaN fast devices compared to the slow old silicon platforms, these on the left-hand side in the red dashes, those were the best in class using silicon. And the price there, those were the prices at the launch of those devices. And you can see by going to the right-hand side, we've been able to reduce the size of those devices And at the same time, the retail cost has come down, almost half the size and almost half the retail price of silicon. So this is a very good time for GaN to increase in production. There's the single device-to-device relationship, but we also can look at how we can use high frequency, small size integration to combine functions as well. So in this case, there's a lot of interest in the iPhone 12 not having a charger in the box. You can buy a GaN device with 3 outputs for almost the same price. So a way of integrating using the high frequency. And a very quick look at the second revolution in power. Back in 1977, Mr. Dan Kinzer was the process expert bringing the HEXFET into the world. And during the next 10 years, there was an amazing leap in efficiency, power density, and reduction in cost, driven by 4 factors of a new switch, new magnetics, new controllers, that's integration, and new topologies. Since then, we had a flattening period where we had some increase, but nowhere near as dramatic. And now, with the arrival of gallium nitride, again, more integration, more magnetics, and new topologies, we see again a big increase in power density, in fast charging, and reduction in cost. And thank you very much for being here tonight for this presentation.
All right, thank you, Stephen. Let's move forward to our 4th presenter, and I'll just remind everybody that you can enter your Q's and A's in, and we'll address them after verbally. We can have the panelists discuss it, and I think it'll be open up some other good questions after all of our panelists are done. So our next speaker is Noah Sturken. He has focused on the integrated power conversion with CMOS for over a decade. Dr. Sturken is a founder and CEO of FERIC, which sells integrated voltage regulator products and related technologies. Dr. Sturken holds a PhD from Columbia University and has over 25 publications and patents, primarily related to CMOS integrated power conversion. So thanks, and take it away. Make sure you unmute yourself.
Perfect. Yeah. Thank you so much for the introduction. All right. So our company FERIC has developed kind of a combination of technologies that enable the integration of voltage regulators, primarily with high performance digital ICs and microprocessors. So, the general advantage that we've identified through the course of development and engagement with our customers is that by integrating power conversion functions as close as possible to their load, there are substantial benefits in terms of size, cost, and area. So generally, if we can shrink our power converters so that they can be co-packaged with a processor, we can reduce substantial conduction losses, we can improve options for power delivery, and find a number of sort of unexpected benefits with power integrity. So of course, it's very challenging to miniaturize power converter. FERIC is doing this with a proprietary manufacturing process that allows us to fabricate thin film power inductors directly onto a given IC. So we have a manufacturing partnership with TSMC where we're able to manufacture single chip power converters that truly have all of the components necessary for that power conversion system integrated. And so then we can offer these power converter chiplets, these package voltage regulators, PVRs, for sale for our customers to integrate directly into the packaging of their processor. And in doing so, realize the significant benefits of integration and miniaturization. So one of the key advantages that a given system, a processor, so forth, is able to realize by achieving a higher level of integration is substantial improvement in power integrity. So by transitioning from sort of the conventional power delivery network where we have a voltage regulator residing on a board, and then we have to, conduct power at a pretty low voltage through a complicated impedance network. That's, I think, probably a very familiar problem for this community, and it's complicated because there's a very complicated low impedance network that needs to be managed across several levels of abstraction in designing that system, right, across board, package, and into the IC. So alternatively, we can offer a single chip power conversion solution that can be co-packaged with a microprocessor. And in doing that, we can, bypass a lot of the complicated resonances that occur in our traditional power delivery network. Further, the integrated voltage regulator that we're able to offer here, it has very high regulation bandwidth. This is by nature of our development of that system. It has these thin film inductors and also operates at a very high switching frequency in order to achieve the dramatic miniaturization necessary to enable the in-package integration here. So we have high switching frequencies, high regulation bandwidth, and that allows us to provide a very kind of simple, low broadband supply impedance for that microprocessor. As we reduce that supply impedance, we're able to reduce the supply voltage margins for that processor, essentially eliminate the resonant peaks that would occur in our conventional power delivery network, and allow that processor to operate more efficiently and with better peak performance. So as a simple example, on the upper portion of this slide, we show an illustration representing a conventional power delivery network with a power IC, inductor, capacitors, and we have a BGA, organic package, some ceramic capacitors in there, and our die. So we'll have resonances associated with capacitance on the die, on the package, and on the board at a minimum. Each of those tend to occur at different frequencies because we have different inductances and capacitances. And so that means when we look at the broadband supply impedance from the perspective of the microprocessor, we see something like this red line shown in the lower left of my slide. So there's several resonant peaks, and we understand that a given load current step at the processor is going to excite those resonances. Alternatively, if we have our package voltage regulator that can drop right into the microprocessor, we can forget about what's on the rest of the board. Our power delivery loop is dramatically reduced, and we're able to eliminate, the low frequency resonances that would occur here. We still have some resonance that's, developed as a consequence of the small inductance, between the PVR and the processor die, and then capacitance on that processor die. But, again, by nature of high bandwidth regulation on that PVR, we're able to reduce the peak impedance that you would see otherwise. So we're kind of, providing some benefit in regulating that final resonance by nature of the PVR's high bandwidth regulation. So as an example, this is kind of a detailed result that we were able to arrive at with a early customer. On the upper half of this slide, we show a load current transient response with a conventional motherboard voltage regulator. So the scale here is on the order of microseconds. We have a large first droop, and then we have a second droop that takes quite a while to recover from. So then alternatively, with the ferric power converter, second droop is gone. We still have some first droop. It's almost impossible to eliminate that, but we've substantially reduced the absolute voltage error associated with the transient, and improved the settling time by a factor of about 40. So that's attractive, and it allows this microprocessor to operate with a lower supply voltage, less supply voltage margin, and consequently higher conversion efficiency. Higher computational efficiency. But that being said, as I mentioned, we're selling these chips now, and finding that these benefits really stand up. There is still some, resonance, some impedance between the power delivery unit, the PVR, and the microprocessor. In addition to, in some cases having challenges with the AC impedance of that loop, some very high performance computing applications have very demanding current density requirements where, bottlenecks in the chip to package substrate interface are actually, the limiting bottleneck for performance on that processor. So forward looking, Ferric's engaged with a handful of customers that are, actually implementing stacked integrated voltage regulators using a combination of our thin film inductors on advanced CMOS, coupled with high density capacitors, coupled with high performance logic device. So these three layers can all be stacked by our manufacturing partner TSMC with their wafer on wafer bonding process that allows for this high level of integration, and really seems to be the best way to circumvent the power and data bottleneck that is occurring at the chip to package interface for a lot of the HPC systems that we've been working on. Getting back to the perspective of PDN impedance, with a stacked integrated voltage regulator, we can dramatically reduce the loop between the power source, the regulator, and the load, to be tens of microns and to be highly parallelized, and also to have very high quality decoupling capacitance kind of directly integrated into the stack. So with this combination, we're able to offer a nearly ideal power supply for these types of systems. A higher capacitance density allows us to bring this resonance down, and then a smaller inductance allows us, to also bring the magnitude down with the high bandwidth regulators there. So I think this is an exciting development. It requires a lot of buy-in from partners, from our manufacturing partner and processor partners who are adopting the technology. But I think it's very exciting to see that there are real implementations of 3D ICs that I guess are increasingly practical or increasingly necessary because of, in this case, the power delivery challenges that this type of product has to compete with otherwise. So I think that's it for my position statement. Appreciate everybody's attention.
All right, thanks, Noah. And that's a really great technical introduction to the integrated VR. So the last position statement will be given by a consumer of integrated power technology. So he's not producing, he's consuming at HP Labs. So Kurt Bresnicker is the chief architect of HP Labs and an HP Enterprise Fellow and Vice President. Prior to joining HP Labs, Kirk was Vice President and Chief Technologist in the HP Servers Global Business Unit, representing 25 years of innovation leadership. Kirk holds 28 US and 10 foreign patents in areas of modular platforms and blade systems, integrated circuits, and power and environmental control. He graduated cum laude from Santa Clara University's Humanities Honors Program with a BSEE. So let's welcome Kurt. Take it away. And yeah,
cool.
See your slides.
Thank you for the introduction. Yes, Kirk Bresnicker from Hewlett-Packard Labs at Hewlett-Packard Enterprise. So I'm a little bit different, as Mike said, more on the consumption side, and I'll be going quickly through a little bit of discovering where we see some of the opportunities. And it's great to bat clean up, especially with all the great stuff, and it was wonderful for me to be reacquainted with real engineering and real electrical engineering with my fellow panelists here. But we want to talk about where we see this opportunity. And I think one thing that you should try and take away is, of all the techniques that you saw today, I think all of them are going to be presented with new opportunities as we chase the bytes from where they are today either in our pockets or in the data center, to a much richer set of interactions globally. So I will try and click and advance the slide. So first question is like, where is that data? And we've gone through successive ages where as the data grows exponentially, and our expectation is that we write as much new data about every other year as mankind has ever recorded. It used to be transactional data, a couple bytes that were the memorializing, when you made a particular transaction. Often you had to make the pilgrimage. In this case, going to Walmart, standing in line, and getting those SKUs scanned at the point of sale terminal. And that was, petabytes maintained in perpetuity for business logic. But then, suddenly it was multiple petabytes from billions of people every single day, and collected from their mobile device, then aggregated in the cloud. Those sort of two edge. There was the edge, there was the mobile device, and then there was the data center where we operated on it. And we worked on efficiencies. And you saw some great presentations today about working about both of those two ends of that continuum. Incredibly valuable information because it was human generated, and we were triangulating that human's behavior with all the accumulated information that we could divine because it was part of this social network. But now we're talking about 40,000 petabytes a day. And that's how much today's 10 million odd connected cars are generating. Now, it is not the same quality. It is just what's coming off of those sensors today. The LiDAR, maybe there's a LiDAR, maybe there's a radar, but most likely it's just some cameras, some other sensors, some ultrasonic sensors. But still, the ratio, what takes 2 billion people to generate is now being generated by 1,000 cars. And as we look forward and to the computational and sensing environment we anticipate, if we get to that real, level 4, level 5. Level 4 is hands off, eyes off car, that you can be taking a nap and the car will safely deliver you to your destination. Or level 5, where there's not even a steering wheel or pedals anymore. But as we looked at that, there's a tremendous opportunity, but right now there's tremendous cost, and there's also the challenge of power. And whether we're talking here about the power it takes to create these artificial intelligence models, and here you can see some of the numbers, for a moderate sized model to be optimized and trained one time takes as much energy, 656,000 kilowatt hours, as much as 5 internal combustion vehicles over their entire lifetime. So that on the training side, producing these models, that is incredibly energy intensive. And that's not really even counting all the energy we spent to gather the data that went into these models. And then when it comes out the other end, and we want to multiply that ability to infer from that model that we have now distributed across hundreds of thousands, if not millions of vehicles, suddenly we see, if we were to take conventional approaches, then that might take between 1 kilowatt and 3 kilowatts per vehicle continuously. And just to put that in context, that means that when we take you out of the driver's seat and you're burning 100 watts of glucose, that we obtain from relatively sustainable, depending on what kind of food you eat, sustainable energy, and we're replacing it suddenly with 1,000 to 3,000 watts of computational consuming power, and that could lop off a third of your range. So suddenly, having someone chauffeur you around, if you're trying to think of the societal impact of an autonomous vehicle, you're going to have to start weighing this off until or unless we take some novel approaches. And I think that's really what we're looking at the labs, is we want to have these benefits of this intelligent social infrastructure. And here we can go into, we've been going into intelligent mobility mainly because it's just such a fascinating intersection. You've got computation, you've got communication, you've got sensing, you've got storage, both electrical and data storage, and you've got a motive function, and it goes where you tell it to by itself. So an incredible opportunity to create a platform, a fluid and intelligent platform that you could pour into an existing city to make a dumb city smart, or talking about that grounds up for tomorrow's smart city. But it does have that cost, and that's really the question of how can we marshal all of these computational approaches and look beyond. And I think the one thing we'll say is that it's not just going to be Moore's law. Here we have 48 years worth of microprocessor data. And the important thing to take away from the picture on the left is that even though the transistor count is continuing to increase, you look at everything else that took a knee in the curve back in 2005 when that first era of scaling, the geometric scaling, the scaling that Gordon predicted ended, and along with the Dennard scaling, that when we made a transistor smaller, it used less energy, ran faster, and it was cheaper. That's a triple word score that we don't have that anymore. Now we're in the second area, equivalent scaling. We're shrinking the area around the transistors. We're folding up those fins into little peaks over the surface of that planar chip. Now there's the question: will we get to true 3D scaling, or it will be it's going to be 3D scaling and computation the way that we see in things like NAND flash today? And that's an if. But even if we were, there's also the question of actually taking that energy that you saw so well described, that trying to, even when we get that integrated efficiency Noah was talking about, how do we extract that waste heat? And given the fact that the total typical power dissipation is flat, even though transistor count has increased and they're not running any cooler, that tells us that we're not powering all those transistors up simultaneously. We're adding complexity to the system. Sometimes we're also adding sideband channels that can be snooped and provide security challenges that we are all now living with. That capability, that means that we're not going to just rely on the transistors. Not really going to just rely on Moore's law. It has to be more novel, and more novel computational approaches, whether it is quantum, optical, neuromorphic, analog being brought back, they also will change some of how we want to understand how the power flows to these devices. The last thing we'll say on this slide is again, we're expecting that we continue to have a doubling of our data, writing as much new data as we've ever written every 2 years. But you see, there's a little wedge coming off of this exponentially growing curve, and that is the difference between the overall projected, and this is enterprise data. You can see this is an IDC study. This is data the enterprise cares about. For the middle of this decade, what we expect is that 3 bytes out of 4 that the enterprise cares about will never ever see a data center. In fact, the term itself, that might become anachronistic, because almost all the data is going to be out there somewhere else. And I think that's where looking at that intelligent mobility solution helps us figure out where that data is going to be. And the important thing there is that tells us where the compute needs to be and where the energy to power that compute needs to be. And so this really much more interesting, dynamic, and broad set of design envelopes. So not just the mobile device we all carry in our pockets and the energy expectations we have around there, not just around the hyperscale data center and its incredibly efficient PUE that we can eke out, and we can talk about everything from high voltage DC to the integrated conversion and those super tight loops that we could get next to those next generation accelerators, not just GPUs, not just CPU anymore, but just that whole gamut of acceleration technologies. And realizing now we need to actually figure out where the compute is going everywhere, from tiny little devices, from embedded devices, all the way up through exascale supercomputing. And I think that's one of these things, and this is sort of how I think of those design envelopes. Of if I was really going to create an integrated intelligent mobility solution, I will want to understand about 7 of these different design envelopes. And I've highlighted some of the energy considerations about each one. But first, that beacon, that sensor, the lick and stick trusted data source. And there, the interesting question is, it's only as useful as its service model. And once it is lick and stick and is able to harvest the energy, perhaps it gets goosed with some induced power when it's actually doing a readout phase. But still, when we get to that ability, that's where so much of that data will actually begin its process of being admitted into economic consideration. The next one up is that access point. What is that farthest edge of the network that today is still on a piece of copper that allows us to deliver power over that copper with something like power over Ethernet. If we move over to photonics and have the benefit that I can launch a photon 10 centimeters or 1,000 meters for exactly the same amount of energy, I have a great capability there in pulling the data off for the minimum number of joules per bit, but can I still deliver that bulk power over distance? I got to think of how that will evolve. There's the aggregation point. What is the smallest computational device I can safely land a Linux container on? This might be that engine control unit, the next generation engine control unit inside of that smart vehicle. And as we continue to make those vehicles smarter, that will grow in capacity. Maybe it ends up being that mini data center. That's the next one of that edged hardened. What is capable of handling, underneath the hood of a vehicle or out there in the desert, in that 5G radio access network control bunker, those hardened environmentals. So how can we do that? And where's that crossover between AC/DC, between passive and active cooling? So between the aggregation point at maybe a 50-watt envelope and this edge hardened system, maybe that's moving up to hundreds of watts. There's an interesting thing there, but again, it's with that hardened environmentals is the extra wrinkle we'll add in. Then we'll have that single system flexible platform, that rack or that tower where I just need that one off. And whether this is industrial control or automation or just that spot I need to have some compute in some area that still is relatively benign, well connected to the network, well connected to grid, but it's now changing in that it's not just the server anymore. It is these accelerators, these next generation memories coming together in that footprint. And what does that tower or rack system, that singleton, look like in the near future? The next one up is that blade system that you heard quoted in my bio, and that's sort of the question. That was an interesting system at the time. It was that a quarter of a rack high, integrated networking, integrated storage, integrated power, modular things you could plug in and out, N+1 grids in, high voltage DC distribution on the mid plane out to those microprocessors. And that's sort of a question: does that one actually survive? Is it too much and yet not quite enough? So I think that's an interesting space to watch in terms of that market. The rack scale, now starting to design where I really want to roll in, plug in networking power, turn on for legacy environments or for novel accelerator environments. More and more people are doing these really interesting accelerators. They're not trying to sell you a PCIe card anymore. They're trying to sell you an entire package system at the rack scale that you wheel in and plug into your network. And whether it's on your premise or on theirs or in a colo, it's that fully integrated rack and it's designed like that. And that allows more degrees of freedom to admit some of these novel technologies at that scale than we've seen before. The next one up is that aisle or pod modular. And here you've seen these, I think, probably the shipping, stacking up shipping containers, all chock-a-block full of what used to be in data centers. And it's an interesting one in that it's a trade-off. It is trying to get something that approaches the efficiency we see at the hyperscalers data center, but still have that flexibility and that build out modularity that allows us some more capability. So it's a trade-off, but this is also where you're going to get that bulk high voltage input along potentially with water cooling, plumbing in big old fat network pipe, and these things will stack and be that environmentally, perhaps more environmentally interesting, especially if it hooks up to things like passive cooling, cooling that doesn't require cooling towers, ambient cooling technologies. And last one we'll add is the sort of pushing the envelope. And you heard Noah talk about this HPC data center and that power density of those next generation CPUs and GPUs next to high bandwidth memories. And although it's not just about the compute, and the little highlighted in red here is 6 picojoules per bit. That's really what the goal of the xScale teams is for, end-to-end energy budget to move 1 bit. And whether you're moving it from one blade to the next blade, one rack to the next rack, or from one corner of the data center to the other corner of the data center, again, that's where the photonics comes in. But a rule of thumb is you want about 8 bits of memory bandwidth for every floating point operation. And so if it's pica times exa, you end up with mega. You end up with megawatts of energy expended just to move the data around. That's not even counting the fact that I want to operate on this data. But operators need operands, and we move those operands through the data center over these fabric elements. So this was just a real sort of a quick swing through what we think is really interesting, is that these edge to cloud service message, that's confluence of three critical supply chains. The ones we're used to, the infrastructure supply chain, the energy supply chain, but increasingly also this data supply chain, that whether I'm pulling data out or putting data and models in, I need to understand the interflow between all three of these. And if I don't have it, then I end up derating somewhere. In the same way we would have derated the frequency of the microprocessor if we couldn't keep up with the frequency response that it's demanding through all of those inductors and capacitors that Noah showed us. That same thing is happening with data. And that's really that AI and ML, as this becomes a pervasive way in which we either compute and inference on the edge, or even to control the infrastructure itself to give us that predictive capability. We'll want to understand how all those data flows. And as this becomes continuous integration, continuous delivery, we should expect that and account for the energy and pre-plumb and expect that we're going to need this to come back out. And finally, the big thing about a lot of this stuff is you can try and do it in a bunch of different ways. You can try and solve everything in the cloud, you'll find that you fail on latency. You can try to solve everything on the edge, you find that you might fail on space, weight, and power, or energy at the edge. And figuring out how to have that balance and design these complex societal infrastructure systems is going to take the best and brightest, not just of the compute, not just of the comms, but of the power delivery too. So that's it.
All right, thank you, Kirk. So before we get to our Q&A, I'd like to thank our sponsors once again, Alliance Semiconductor, as well as Navitas, and as well as our IEEE co-sponsors, and that's the Santa Clara Valley EPS, or Electronics Packaging Society, as well as nationwide IEEE PELS, IEEE EPS, as well as PELS TC2. So those are all IEEE groups associated with the talk. So thanks. And I mean, all electronics is pretty much tied together. So what we're going to do is just go through the question list. Brian and I we'll take turns answering or asking questions off the list. Brian has some good things, and I think if the panelists would like to answer them as they see fit, they can unmute themselves and do so. So I will just kick it off. Brian, you want to kick it off?
Oh. Well, no, just one comment too. I'll ask the panelists. Now it's time for the pretty pictures to go away. So let's make it feel like a panel for our audience. If you can, to please start your video, and let's lift the COVID veil here. Let's not be a hypocrite. I didn't shower this week for nothing. All right. Good to see you all. Thank you. Go ahead, Mike, if you wanted to start one off.
Okay. Let's see. This is a good question. This is a switch capacitor converter question. So this will be for Won Young and Steve. So could you talk about the trade-offs if you place the buck in the first stage and the switch capacitor in the second stage? It seems like you could shrink the inductor size if you did this, since it would see less current. Plus, you could use low voltage FETs for the SC and run at a pretty high frequency.
I think I can answer that one. So it is a good question. You can put inductors at the front of a charge pump. However, we're using the inductor for a number of reasons. The charge pump on its own is very inefficient. And it's inefficient because when you close the switch between two capacitors that are at different charge states, you're losing energy and you're seeing a big inrush current. It generates EMI and losses. We use the inductor to act like a current source to actually restrict current flow through the charge pump, so that instead of seeing these big peaks and a lot of noise, we see effectively an almost constant current moving through the charge pump. And also the other thing is that there's what's called charge redistribution losses, which is within a charge pump, you generate quite a lot of losses due to imbalances in the capacitors. And the third point is the charge pump itself, the amount of ripple that you see on the charge pump is dependent on the size of the capacitors. What we do is we allow the charge pump to actually generate quite a lot of ripple, and we use the downstream buck to effectively regulate out all that ripple, okay? And the inductor in that buck stage is where we absorb all of those charge redistribution losses within the charge pump. And because it's in the output path, on the output side of the charge pump, that's energy that can be recycled into the output. If it was on the input side, it would be lost. So basically what we're doing is using the inductor to control current flows through the charge pump, and also pick up all those charge redistribution losses that we see throughout the charge pump, and basically put it through to the output as a regulated power, rather than wasting that energy. And it makes a difference. It's a charge pump, if it's just fully discharged cap and then fully charged cap, and it goes a switch, is 50% efficient. You can get higher efficiencies if you're moving the voltage much smaller amounts. So if you're almost fully charged cap going into almost a fully charged cap, you can get a better efficiency through that charge pump. But you're still getting some losses due to imbalances in the charge pump. And what we can do is take all those imbalances, dump them into that inductor, and then use that energy to the output. So that drives up the efficiency, and it can effectively halve those losses that you would see within a charge pump. We can still do things. There's all sorts of combinations that you can play around with this architecture to put inductors on both sides, and all other kinds of combinations. In fact, if you look to Google's own switch tank architecture, they put inductors in every other arm of a charge pump. So it's a asymmetric architecture that they have, using inductors throughout the charge pump. So there's many ways you can use inductors, but just placing them at the input isn't going to help you with all those additional losses that you see. Hope that answers the question.
All right, that's a good answer. Won-Young, do you have anything else to add?
Oh yeah, just one quick thing is, yeah, so it's interesting because we actually, in our initial years of our company, we had started the company with that kind of topology where the inductor is at the input. And so if it's just a simple like buck and downstream switch cap, I think one of the downside is that the buck would need high voltage FETs because it needs to block the entire VN. We had developed a topology that could utilize low voltage FETs, so it's not really like a buck and switch cap in series. But that also had its own issues. So honestly, I'm not entirely sure like what's the right answer. I think it depends a lot on the application and customer needs.
Okay. All right, thanks, Won-Young.
Okay, did any of the panelists have another comment on that topic? Anything? Okay.
Sorry.
Oh,
can I add
yes,
a comment,
Joe.
Brian? Yeah, so I think another reason to have the buck stage at the end is because the buck stage is what's providing all the regulation, and you want the regulation as close as possible to the load itself to provide the best possible regulation. So if your buck is doing the regulation, that's just, you'd want it at the end.
Okay,
right.
That's a good answer. I think it also kind of
Joe.
addresses the next question on the list. So anyway, Brian, you want to choose one?
All right. Yeah, and actually, just before that, I want to remind everyone too, in case you're asking, again, everything will be made available, from a recording, full recording of this webinar, to also, PDF of the presentations that all the presenters made and graciously agreed to. So don't worry, you'll get that, and you'll be emailed that, just like the link was because of your Eventbrite registration. So I'd actually like to, I had just one, I was thinking about this the other day, and I think this actually addresses maybe a handful of things. I'd like to know kind of the panel's opinion on how much of the integration roadmap you think is related to packaging versus topologies, right? Because obviously they both play a very large role, and the level of integration, especially if you want to go to the next level of, when are we going to start integrating these power solutions directly with the loads, whether it's monolithically or through some heterogeneous integration or 2.5 or 3D packaging and all that. So basically packaging roadmap versus power electronic topology roadmap. What's moving the needle?
I'll take that one if I can. That was Steve.
Please, sir. Steve-O, go for it.
Thank you. I think it's the topology drives the level of integration, and it's specifically the frequency of switching in the topology. So if you're running at 1 kilohertz, then you've got a chunk of energy that you're sloshing about in the circuit, and integration is not going to help you. And the system itself doesn't hinder the frequency because you're low frequency. But if you get up, at least in the AC-DC conversion area of say a megahertz, then you've got to start to integrate things in a small area, i.e. co-package things. And then obviously, as we're doing, it's the monolithic integration of the drive stage with the power device to eliminate the impedance of that loop. So I would say topology influenced by the frequency drives the scale of integration.
Okay, interesting. Anything else?
I think the kind of to add on to that, the high frequency buck converters are going to be the best way to get the best regulation performance, and you need more advanced packaging in order to take these chiplets in the heterogeneous integration that you suggested to get those as close as possible to the load, right? So that packaging developments are enabling that heterogeneous integration, right? Without that, you couldn't get as good regulation performance generally. So I think that doesn't necessarily require a topology improvement, right? But in that case, the packaging is kind of helping along there, along with the advancements in the inductor technology that enables that integration, right? So in some ways, you can consider that also a packaging improvement, right? We're getting inductors right on a CMOS die.
Yeah, certainly. Thank you, Joe. Well, that's good. I'm glad I didn't go with my first question, which was asking why nobody on the panel seems to support integrated power solutions, but that could have been awkward. So I'm glad we didn't go there.
Actually, I would argue that their integrated power has a place to play. It's actually touching on what Joe has just said, which is that it's all down to parasitics. You can run a very high frequency if you want and shrink things to trace inductance and massively parallelized capacitance within a piece of silicon. You can do it all on board if you want. But parasitics is critical here. And so that tells you have to go to packaging if you want to get to those very high frequency, fully integrated types of solutions. It's all down to parasitics. It's all down to how much EMI you have in your system and what the voltage tolerances that you're also wanting to see on your piece of silicon.
Yeah, as you were saying that, Steve, you kind of reminded me. I thought back, 5-6 years ago when I was in discussions like this or things like a PSoC workshop, it felt like everything was about, switch cap versus coupled inductor. And now, not seeing much, I don't hear much of that. So that seems to have changed a bit too. And, I don't know if it's one more to do with the resurgence of wide bandgap or other things, but yeah, interesting. Any other comment from the panel, Kirk?
Yeah, so I think it's interesting to see the heterogeneous integration really across so many of these aspects, whether it's integrating photonics, relegating that electronic transmission from millimeters to perhaps just microns, that we want to shrink all of these loops down as close as possible. And to realize that, I had made this comment in the abstract I sent you, is that the last page of Gordon Moore's seminal paper, he talked about that need to build up from smaller building blocks. And I think what's really happening now is that realizing it's not just smaller logic building blocks, it is smaller building blocks across all the disciplines that need to come together for one of these complex systems really to continue to progress along that exponential scale, so that as the data grows exponentially, as our time to realize insight from it is decreasing exponentially, and as we realize that we need to have this be sustainable, so that it's in fact equitable for us to design these systems, then we're gonna see more and more of this heterogeneous integration, relegation, minimization of parasitics, until they're designed out, because we've done more and more. And so things like wafer to wafer bonding and wafer scale in 2.5D or 3D is not going to just be about getting the high bandwidth memory next to the GPU, next to the CPU on that substrate. It's going to be the photonics, the power, all of these things coming together at that silicon scale of integration.
Yeah, okay, thanks, Kirk. You can almost say it's like a system of systems or something like that.
Something
Wink,
like
wink.
that, a miniaturized silicon. So all those things we used to do about at the PC board level, and now it's at the silicon scale, and also bringing in the fact that is now so much more is delivered soft, in that it is continuously updated. That element of software in so many of these things, that dynamicism, now achieved through these control loops that are perhaps all gonna trying to understand the benefit of machine learning.
Yeah, thank you, Kirk. Did any of the other panelists have another comment on that? Otherwise, I'll kick it back to Mike to address the next one. All right, Mike, looks like you're a winner.
All right, so here's a question from Sasha. What are the key drivers for the reduced entry cost with GaN chargers?
I guess that one's for me. Can you hear me, guys?
Yeah, we hear you,
Okay.
Steve. You're right. That's yours. You win. Go for it.
Thanks. Okay, so the fundamental thing actually comes back to topology and frequency again. So as you go higher in frequency, and obviously you adopt more advanced topologies, then things shrink. So when you go from a typical, what's called a flyback, usually a quasi-resonant flyback topology, running at say 50, 60 kilohertz, and you go up to an active clamp flyback, which is a soft switching two-switch topology, running at 500, 600 kilohertz, you can really switch from quite expensive, large, heavy toroidal or wound transformers and go to what's called a planar transformer, where you've got two pieces of ferrite clamped to either side of a PCB, which also acts as part of the EMI filter. You reduce the size and the weight of the EMI filters. You can also reduce the size and cost of the output caps. And then depending on your topology, you can also throw out the bulk caps as well. And by going to more modern topologies, you have an inherent higher efficiency as well. So you can then reduce heat sinks, reduce the case size. So it's a positive spiral of using frequency to reduce size and reduce cost.
All right. Thank you, Steve. Any other questions, comments? All right. Let's see. So yeah, actually, so here, like one that, and maybe this is, I guess, more of a question for perhaps Ferric and on the on the integrated magnetic side of things. But so we have someone asking about Max Yu is asking about the switching frequency of your PVR and the dynamic volt scaling capability and all that. So maybe if you can, since we've kind of commented more on that aspect from a switch cap perspective, maybe you guys can elaborate a little bit on the PVR perspective.
Yeah, so the switching frequencies for the Ferric PVRs, they can range from 80 megahertz to around 200 megahertz, depending on the different voltage regulator that we're using. Certainly, a big advantage of this is performing dynamic voltage scaling much faster than you could otherwise. We include buses that allow you to write new voltage commands into our chip to scale the voltage faster, just from a latency perspective of getting a new command in. To answer one of the other questions about needing the inductors to perform the regulation instead of just the capacitors, the inductors allow you to use pulse width modulation techniques, a rather standard control technique for buck converters to modulate the voltage, whereas a lot of these switch capacitors designs are typically a single conversion ratio, like 1 divided by 4, 1 divided by 2, something like that. With regards to the dynamic voltage scaling, we've shown that by performing dynamic voltage scaling, by moving voltages on the order of 100 nanoseconds or so, you can save power, like overall system power, upwards to 30% compared to a system that's performing dynamic voltage scaling just at a couple microseconds scale. Certainly you need interaction with the load die, you need the load die telling you how to move around the voltage optimally to get those sort of system power savings. But I think this kind of shows that in general, the two-stage architecture where you have the switch cap or other sort of resonant converter doing most of the voltage step down, and then a faster buck regulator performing the better power management features is kind of the optimal overall power architecture for a lot of these kind of more advanced systems moving forward.
All right. Thank you, Joe. Is there any other follow-up comment or anything from the panel?
I'd like to just add a little comment there, which is very much supporting what we just heard, which is it's a startling fact that with the exception of, let's say, Intel AMD processors and a few others that are using adaptive voltage scaling, typically most silicon out there is about 40% overpowered, 20% over voltage, just to deal with the fact that silicon vendors have to make sure that they can sell most of the silicon they have and it fits within the guard bands. So dynamically scaling voltage to suit the specific piece of silicon under its given conditions, both for process variation and temperature, can on average save about 40% power for all pieces of silicon that are out there. It's a massive opportunity. And the only way you can get to that is to get that power conversion, not only just interacting with the load, but also right up close to the load too, because there's a dynamic element here. If you've got too much impedance between the power and your load, you're never going to get the full benefits of that power savings. So bringing it right up close to the silicon can make a massive difference to power consumption, which comes back to, the HP picture. There's a lot of power out there going to be consumed. How do you help it? Well, there's 40% sitting right there for most silicon, right the way down to consumer level products, IoT stuff and stuff like that. So we've got a lot of work to do to get power working more intelligently with the load.
Okay. Agreed. Anyone else on the topic? All right, Mike.
All right.
Thank you.
I'll ask a question from Ada. This is specifically to Ferric, I guess, but I guess it could be addressed by any of the switch cap converters as well, because they're also close to the load. She's wondering, are there any special tricks required outside of traditional filters for managing noise from interfering with the load, since their IVRs are so close? So I guess broadly, do these converters have any different properties, or do you need to do something different to filter the outputs compared with normal bucks?
I think the biggest difference is that we're operating at that much higher switching frequency, right? Having that higher switching frequency means that your capacitors are just going to have a lower impedance for a given amount of capacitance, right? And so they'll do a better job filtering whatever inductor current ripple that you have in your converter. I think additional topology decisions like using multi-phase buck converters can get you further cancellation of your inductor current ripple and subsequently your voltage ripple. These are, rather standard, but they do a lot to help with the amount of noise that you have right at your output. And they push all of the noise to a higher frequency where you don't need quite as much capacitance in order to filter it.
In addition to that, conceptually, the AC current that's flowing through this power converter as it's operating periodically, that entire AC loop is on our chip. So it's in a very small area, and that, by nature reduces any radiated EMI, allowing actually for a much cleaner supply. And we've had customers essentially identify that a little bit unexpectedly, that they have much cleaner supplies, all the way up essentially to our switching frequency than they would see even with some LDOs. I guess maybe not great LDOs, but that's again, consequence of the small loop. Yeah.
Any spread spectrum in there, or dithering or something like that? That maybe helps.
Yeah, it does. Yeah.
Okay,
that does work too. Yeah.
Any other comments? Okay. I'll move on. I see there's one here from Bill Chen. I'm assuming I think it's the right Bill Chen, who actually is also a co-chair of the Heterogeneous Integrated Roadmap for the Packaging Society. So he has, I think you'd have an interesting perspective here, and he directed his question at Kirk, but it's a simple question. Well, it's an open question, but that's why I prefaced it with the person asking it. So he says, Kirk, you talked about energy balance. So what do you expect to find? You're on mute, Kirk.
I'm sorry, could you repeat the question? I couldn't hear you clearly. Energy.
You just said that you talked about energy balance, which, you could take poetic license and go in lots of different directions from that. So why don't you elaborate for us on, how you're balancing the force, whether it's at the chip system or network level.
Yeah, okay. I understand the question now. Yeah, and part of this is the question of I have an information life cycle. I acquire information, I assure that it is valid, I analyze it, I gain insight from it, I take action, and that's a loop, because every time I take an action, I generate more data, and everything cycles again. And that time cycle of the time cycle of that loop is sort of, how long do I have for this insight to still be viable, to still be interesting? How much energy goes into it? How much infrastructure needs to be there? And balancing all those things out, that's sort of that question. Is it a benefit to me to do all my computation at the edge, knowing that it might be harder for me to get the energy and to get the infrastructure out there? Can I just have, the way one of our technical committee of our board directors told me, it's like, tell me why the whole world isn't going to be dumb sensors and public cloud, and that's it. And everything else in between is just spectrum to get the dumb sensor data into the cloud. And there's really sort of three things that keep data at the edge and make compute want to follow it out there. And that's physics, that is economics, and that is law. So any one of those three things, or usually an interesting combination of those, will factor into the decision about where we want to host that information lifecycle. And as they become increasingly complex, as they're interlocked, and I love what Stephen Allen just said about that, that precision that we're seeking. As we're trying to not live by the, be dominated by the tyranny of the average. And as much as we love our Deming quality control and that statistical sample, we are sort of approaching the age where perhaps we can be intimately connected with every one of the millions of the devices that shipped from our designs, and have that active control that's based on all this data. So I think a big piece of this is trying to understand, how do we create the ability to make these trade-offs? I want to put so much compute inside of the 1 billion edge devices. I want to put so much compute inside of the 1 million aggregation devices. I want to put so much compute into the 10 hyperscale data centers, and figuring out how all of those things interplay for a specific application is some pretty advanced math that I think we still need to work out as we talk about these systems, especially again, where it's not just about the infrastructure, it's not just about the energy, it's also now about the data that flows and how those three things interlock.
Thank you, Kirk. Anyone else have a comment on that? We'll go debate style now. Steve Allen, it seems your name was evoked.
Yes, it
So
was.
you get 30 seconds to respond.
30 seconds to respond. Well, I totally agree. I think we have to start thinking in very fine granular detail at every step along the way. Datacomms is a very good example, but I think it's much more than that. All kinds of systems, you need to kind of bring things close to where the power is being consumed, where the computer is going on. And so integration, the whole point of this discussion today is, talking about integration. It's not just packaging, it's bringing power, it's bringing computation all together. We're still kind of taking baby steps, I would say, in the industry. Intel, once upon a time, just talked to the processor. Now it talks to the memory, and those things talk together. But it's still kind of a bit disaggregated. There's a lot more that can be done to bring this together into a common system. And I think you can find plenty of examples across all types of platform, whether it's mobile, right the way through to a data center, where we need to really think out of the box. How can we really make things a lot different here by integration, and break it down to individual specific things like, okay, that chip is consuming too much power. How can we reduce it? What can we do to help drive the power down? Memory is a very good example. There's right now specs being drawn up to put memory onto the DIMMs in the DDR5. But what about putting it inside the DIMM? Because memory is a massive consumer. It's the second largest consumer on a compute platform today, other than the core processing, right? A lot more that can be done, and that can only happen with integration. So I totally agree. You've got to look at it every step of the way to see what you can do to improve what you do. So it's more than 30 seconds.
It's all right. We don't respect the debate commission anyway, so don't worry about it. Thank you for that, Steve. Did anyone else have any other comment or anything? Actually, I think Steve kind of segued to something that I think is another maybe really interesting point about, just the panel's thoughts is, so yeah, eventually we're integrating everything to power. And like you said, ideally, eventually, right, power will be essentially invisible. I remember joking that when I started doing power stuff at HP, 15, 17 years ago, that I remember thinking by the time, I have a child that's an adult, I should have to walk them into a museum to show them what daddy worked on, because you won't be able to see it physically anymore. So, what do you guys think about integrating, taking it to the next step, whether it's heterogeneous, homogeneous integration, but like truly integrating with the load? Is it more of a technical feat versus a supply chain stakeholder, cooperation, or is it too many cooks in the kitchen, so it's impossible? What do you guys think?
Hey, I feel like one of the really big, maybe like practical challenges is that, this might be just in mobile, where basically they're moving to new process nodes for almost every generation. And what I hear is they basically have one revision that they can do before going to mass production in a new process node, in a new processor chip. So even if they feel okay, IVR is a way to go, it is really challenging to put it in and say, okay, we're going to get this right in one revision. So this is just, I don't know, maybe it's just one practical challenge I see
Well, I think that makes a lot of sense. It's like the processor company makes a processor. They're not, gonna want to sink their whole effort because they're, taking on a lot of risk for the power supply. So I think for that reason, regardless of the sector, it's normal for people to be, especially risk adverse with the power supply. Like if you integrate the wrong power supply and the thing fails, you'll get fired for sure, right? So So it just takes a long time. I think it requires maturity and persistence, but it's very natural, right? There's consensus among this panel that integration adds value. It's just a matter of time and risk and persistence, I guess.
I think one of the
Gotta love the irony there, Noah, that you mentioned, someone like Intel. Bear in mind, the guy you responded to came from Empyrean, right? So follow Empyrean, Altera, Intel. Intel actually now owns that today, but that's a different full circle story. But
yeah, well, he's persistent. He'll probably be able to sell another company to Intel.
I'm sorry, Kirk, you had a comment.
Yeah, we are at a very interesting time. We have about 5 years left on the Moore's Law equivalent scaling roadmap before that flattens out. And there's an open question. Will we have three-dimensional, and I'm talking here inside of the die, will we have three-dimensional scaling in compute the same way we have had now in memory? Memory arrays are very different than computational arrays. They have redundancy, they're easier to repair, they're lower energy density, all these things that compute isn't. And so that's sort of an if, not a when. And it means that we've had this tailwind behind us really since the 70s on, even though it changed in 2005, became a different tailwind. One picked up just in time as one died off. If that doesn't happen this time, then that's really one of these things where real innovation is admitted in, where the risk of inaction, of obeying the conventional system way of doing things is put up for bid, and being able to defy convention is economically admitted. So as we get to these things, and right now I think we have two things that are fascinating. We have the Moore's Law as it's flattening out potentially. At the same time, we have this new switch to these fundamentally data-driven. It's not about programming, now it's about training. These data-driven applications that want to voraciously consume all this data that may never be centered. They may be out there. So I think, again, that's where, the interesting times is all these things happening simultaneously.
Fair enough. Interesting times is a good characterization. Did anyone else have any comment there before we move on? All right, Mike.
Okay, so I have a question. This will be kind of a combination of several questions on the board. What about silicon capacitors? And either this is capacitors on a standard IC process, or deep trench capacitors, or there's been mention of TSMC very high power density capacitors. Are these interesting? Are you using them? Do you see uses? What applications do you see uses in? And this could be for switch cap, or it could be for a ferric type application. So several people should get a shot here.
Coming from Murata, I guess I can maybe answer from their perspective. We have silicon caps available. For power conversion, they're not really there yet as far as capacitance density, voltage rating, too high ESR. So they're not really ideal, even in a charge pump, where you get real benefits with silicon caps. There's no DC voltage bias. There's no temperature impact to capacitance. So they're really perfect for charge pumps, but they're just not there as far as energy density. So for power, there are other substrates which makes more sense to build capacitors on. It's all about surface area. You can do that without silicon. Silicon's also very expensive. So right now, I'd say it's a little ways out. Where it does have advantages in low power, massively parallelized systems, particularly in low power, things like optical. That's where we see silicon capacitors are being used a lot there. Anything where it's very small amounts of capacitance, very high level of integration, that's where it can be used.
Yeah, I think the silicon capacitors generally have superior ESL performance, at least when you're able to have specific terminations that you can place in a way that lines up with your other devices. You can just drastically reduce that ESL and get better parasitic performance generally. It's almost as good, maybe not quite as good, but almost as good as having additional capacitance right on your die. and that makes a lot of a big difference when talking about that first droop in all of your different resonances in your power supply and your PDM.
So I think silicon caps, so the first thing is they're already, I think, production proven. So so they're not used in switch capacitor power IC as far as I know, but they are already used in like hundreds and millions of processors as decaps, actually. So they are like pretty high quality, production proven. That said, like at least for our application where we're targeting like as high efficiency as possible, like Steve said, the energy density isn't there yet. So we would prefer to use MLCCs that have higher energy density. But then I think silicon caps can have a market even now with the lower energy density than ceramic caps, where the Z height matters a lot. So like MLCCs, the Z height would be somewhere like around 1 millimeter, whereas silicon caps, if you extend the wafer, it'll be like, I don't know, 200 micrometer or something. So if there's applications where like that thickness savings is very, very important, you are willing to sacrifice the energy density, then yeah, I think there can be a market like even currently. Okay. Yeah, thanks. I think we might have, Brian, do you have a question you want to go for? With the last minute or two?
Yeah, nothing pressing. That's a quickie thing. But yeah, I did want to also just say thanks a lot, guys. Lots of fun, good discussion, and I want to remind everyone too. We appreciate our sponsors, especially Navitas and Lion, so that everyone in attendance realizes that that's why we can make this free and available to you. So thanks to them for that. And again, just be reminded, you're always registered, which is everyone. You'll get a notice about the when we'll make the stuff available. But full recording and slides will be made available. And then I just want to make sure too. Thanks again to a lot of work under the hood from our other co-sponsors from the local EPS chapter. And SCV as well as the society level, the PELS and Packaging Society EPS gave us a lot of support, and PELS TC2 for their supporting their webinar series. So thanks a lot to all you folks for making this all together and making it happen. It's good stuff.
Thanks to Brian and Mike.
No pleasure.
All at once.
Thanks for having us.
Thank you.
Thanks, everyone.
Stay safe, guys.
Bye.
Bye.
All right, everyone, stay safe and healthy. And there's nothing to debate here, so go enjoy the debate.
Bye.
Bye.
Goodbye.